The thing that decides how the universe ends is getting weaker. That is not a claim from the fringes of physics. It is the current reading of the largest map of the cosmos ever assembled, built by more than 900 researchers across 70 institutions, using a telescope in the Arizona desert that has spent 5 years doing almost nothing except counting galaxies. And if the reading holds, then the standard model of cosmology does not need adjusting. It needs replacing. I want to be careful here, because this is a story that has been badly told almost everywhere it has been told. There is a version of this where a heroic instrument overturns Einstein and everything you learned is wrong. That version is not true, and it is not even the interesting version. The real story is messier. A signal appeared where nobody expected one. It should have faded when more data arrived. It got stronger instead. And then a second group of physicists started pulling on the thread and found that the whole thing might be an artifact of comparing two rulers that were never quite the same length. Both of those things are still true at the same time. That is where we are. So let me start with what dark energy is, why the word constant is doing all the work in this argument, and what it would actually mean if the constant turns out not to be constant. In 1998, two rival teams were doing the same experiment. One was the Supernova Cosmology project, led by Saul Perlmutter at Berkeley. The other was the High Z Supernova Search Team, which included Brian Schmidt and Adam Rees. Both teams were hunting a specific kind of exploding star called a Type 1a supernova. These are useful because they all detonate at roughly the same brightness. If you know how bright something truly is, and you can see how bright it looks from here, you can work out how far away it is. It is the same logic as judging the distance of a car at night by how dim its headlights appear. Both teams expected the same answer. Everybody did. The universe was expanding. That had been known since Hubble, and gravity should be slowly putting the brakes on all the matter in the cosmos, pulling on all the other matter. The only real question was whether the deceleration was fast enough to eventually stop the expansion and pull everything back into a collapse, or slow enough that it would coast outward forever. Getting the answer required patience of a kind that does not photograph well. A Type 1a supernova outshines its entire host galaxy for a few weeks and then fades. You cannot schedule one. You photograph a patch of sky, wait, photograph it again, and subtract one image from the other to see what changed. Both teams were doing this across thousands of galaxies at once, chasing a handful of detections per run, then racing to get spectra before the light died. The supernovae were fainter than they should have been, not by much, but faint means far, and far means the expansion had not been slowing down. It had been speeding up. That result won the Nobel Prize in 2011, and it left physics with a problem it has not solved in the 28 years since. Something is pushing space apart, and it is winning against the gravity of every galaxy in existence. Nobody knows what it is. We gave it a name so we would have something to write in the equations. We called it dark energy. It accounts for roughly 68% of everything that exists. It is, by a very wide margin, the dominant component of reality, and our entire description of it consists of a placeholder. The simplest possible description, and the one that has been the default for 25 years, is that dark energy is a property of space itself. Every cubic meter of vacuum contains a fixed amount of it. Make more space, and you automatically get more dark energy at the same density forever. Einstein had actually written something like this into general relativity back in 1917 for entirely the wrong reason. He wanted a static universe, so he added a term to hold it still. When the expansion was discovered, he removed it, and by one much-repeated account, he later called it his worst mistake. Then, in 1998, the term came back, with the opposite sign and a very different job. Physicists call it the cosmological constant, and I want you to sit with that word because the entire argument I'm about to describe lives inside it. Constant means it does not change. Not with time, not with temperature, not with how much the universe has expanded. 10 billion years ago, the density of dark energy in a cubic meter of vacuum was exactly what it is in a cubic meter of vacuum right now. That is not a small side detail of the model. It is the model. It is the reason we can tell you how the universe ends. Physicists do have a way of asking how constant it actually is, and it is worth understanding because every headline about this result is secretly about one number. For any substance in the universe, you can compare its pressure to its energy density. Ordinary matter has essentially no pressure, so that ratio is 0. Radiation comes out at 1/3. A cosmological constant, a dark energy that never changes, has a ratio of exactly -1. Negative because this is a substance whose pressure pushes outward rather than resisting compression, which is the whole reason it can drive space apart. So the entire question reduces to a measurement. Is that number -1? And does it stay -1 across cosmic time? If it does, Einstein's version stands and the textbooks are fine. If it drifts, even slightly, then dark energy is not a property of empty space. It is something else, probably a field filling the universe, slowly rolling downhill toward a lower energy state. Physicists call that family of ideas quintessence, and it has been sitting on the shelf as an unloved alternative for about 25 years, because there has never been any reason to prefer it. Because if the number is fixed at -1, the ending is already written. Expansion accelerates. Galaxies outside our local group cross the horizon and disappear from view one by one. The last of them slip away in about 100 billion years. Star formation runs out of gas. The final red dwarfs burn down over trillions of years. Everything cools toward the same temperature, and the universe ends not in fire, but in a very slow, very cold silence. That is the standard prediction. That is what is in the textbooks. Now here is what the data is starting to say. The instrument at the center of this is called DESI, the Dark Energy Spectroscopic Instrument. It sits on the Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona, a telescope that first opened in 1973 and has been rebuilt around a very specific obsession. At the focus of that telescope, there are 5,000 optical fibers, and each one is mounted on its own tiny robot. Roughly every 20 minutes, all 5,000 of them reposition themselves to catch the light of 5,000 different galaxies. Then they do it again and again. Since May of 2021, night after night, that machine has been vacuuming up the spectrum of everything it can reach. Nobody is standing at an eyepiece. The whole thing runs as an industrial process, and the number that matters is throughput. On a good night, DESI collects the spectra of well over 100,000 objects, most of them galaxies, whose light left before the Earth existed. It does not care what any individual one of them looks like. It cares where they are. What it is measuring is not brightness, it is sound. In the first 400,000 years after the Big Bang, the universe was a hot plasma, and pressure waves moved through it the way sound moves through air. Those waves traveled outward from every overdense region. Then the universe cooled enough for atoms to form, the plasma cleared, and the pressure vanished. The waves stopped where they were and froze into the distribution of matter. That left a preferred distance. Galaxies are very slightly more likely to be found about 490 million light-years apart than at any other separation. It is a faint statistical bump, invisible in any individual pair of galaxies, but rock solid across millions of them. And crucially, we can calculate how big that bump should be from first principles, which means we have a ruler of known length scattered across the entire observable universe at every distance, and therefore at every epoch of cosmic history. Point the telescope at galaxies nearby and measure how large the bump appears. Point it at galaxies 11 billion light-years away, and measure it again. Any difference in apparent size tells you how much the universe expanded in between. Do that in enough slices, and you do not just get a snapshot of the expansion. You get its history. By April of 2026, DESI had finished its planned 5-year survey with more than 47 million galaxies and quasars mapped. It is the largest three-dimensional map of the universe that has ever existed, and it reaches back across roughly 11 billion years. The first results came out in April of 2024, and they contained something small and strange. When the team fit the expansion history, the best fit was not a cosmological constant. It was a dark energy that had been slightly stronger in the distant past and was slightly weaker now. The preference was mild, around 2 standard deviations, which in this field is barely worth a raised eyebrow. 2 standard deviations means that if there were no real effect at all, you would expect to see a fluctuation this large, roughly 1 time in 20 by pure chance. Flip a coin 20 times, and you will get a suspicious-looking streak. Cosmology has been burned by 2 sigma results more times than anyone likes to admit. The usual and entirely correct response is to wait for more data, because random flukes get washed out as the sample grows. Almost everybody assumed that is what would happen. Get another year of galaxies, and the wobble would settle back onto the flat line where Einstein's constant lives. It did not settle, it sharpened. In March of 2025, DESI released its analysis of 3 years of data, roughly 15 million galaxies and quasars. The preference for dark energy changing over time had grown. Depending on which supporting data sets you combine with it, the significance now sits somewhere between 3 and 4 standard deviations. 3 sigma is the threshold where physicists start using the word evidence. 4 sigma is roughly a 1 in 16,000 chance of a fluke. Neither is the 5 sigma standard required to claim a discovery, and I want to be honest that this distinction matters enormously. But going from 2 sigma to 4 sigma with more data is exactly the opposite of what a statistical fluke does. Flukes decay. This one grew teeth. And the shape of the result is what makes it uncomfortable. The data does not just say dark energy is a bit different from what we assumed. It says dark energy was more powerful in the early universe than a cosmological constant allows, and that its influence has been fading, and that the fading is happening now in the recent cosmic past, in the era we can actually see. Endert Andrade, one of the researchers at the University of Michigan who helped interpret the year 3 results, described it as watching human understanding of the universe change in real time. That is a very restrained thing for a physicist to say, and it is doing a lot of work. Because if dark energy is weakening, then the entire far future of the universe is unwritten again. A constant dark energy gives you an eternal, accelerating, freezing expansion. A dark energy that decays gives you something else. If the decline continues, acceleration slows, galaxies stop receding from us quite so ruthlessly. And in some versions of these models, if the decline goes far enough, the push can eventually turn into a pull, and an expansion that has run for 14 billion years could stop and reverse. It is worth being concrete about how different those two futures are. Under a fixed cosmological constant, an observer in the Milky Way 100 billion years from now looks up at an empty sky. Every galaxy beyond our own merged local group has been carried past the horizon by the expansion, and the light they emit after that point will never arrive here. Not because they are too faint, because space between us is growing faster than their light can cross it. Any civilization that evolves in that era would have no way of discovering that other galaxies exist, or that the universe was ever expanding, or that there was a Big Bang. The evidence gets deleted. Under a dark energy that fades, that deletion slows down or stops. More of the universe stays observable for longer. And at the far end of some of these models, the arithmetic reverses entirely. Expansion stalls. Distances start shrinking. Everything that has been flying apart since the beginning comes back together. I'm not telling you the universe is going to collapse. Nobody has shown that. The point is narrower and stranger than that. For 25 years, we have been able to say with real confidence how this all ends. And the confidence came from one word, in one term, in one equation. If that word is wrong, we do not have a different ending. We have no ending. We are back to not knowing. There is also a much older problem that this touches, and it has been quietly bothering cosmologists since the beginning. It is sometimes called the coincidence problem. Matter density falls as the universe expands because the same amount of stuff spreads through more space. A cosmological constant does not fall at all. So there is exactly one era in the entire history of the universe when the two are roughly comparable in strength, and by an unexplained accident, we live in it. It is like walking into a room at the precise moment two vehicles traveling at completely different speeds happen to be side by side. Possible. But you would want to ask why. A dark energy that changes over time is one of the few ways that coincidence stops being a coincidence. So that is the case for... Now, here is the case against, and it is stronger than most coverage of this story admits. The DESI measurement of the sound wave ruler on its own does not produce this result cleanly. The signal for evolving dark energy shows up when the ruler data is combined with other datasets, and the biggest of those is the type 1a supernovae, the same exploding stars from 1998. And there are three major supernova compilations available: Pantheon Plus, Union 3, and the Dark Energy Survey 5-year sample. When you swap one for another, the strength of the result moves. That is the first thing that should make you cautious. A real physical effect in the universe should not care which catalog of stars you happen to pick up. And there is a structural reason to be nervous about combining datasets at all. Each survey has its own calibration, its own instrument quirks, its own assumptions buried in the analysis pipeline. When you fit them together, you're implicitly asserting that all of those assumptions are compatible. If two of them are each off by a small amount in opposite directions, the combined fit will not tell you that. It will absorb the mismatch by adjusting the physics, because the physics is the only thing in the model you have allowed to move. You will get a confident, tight, wrong answer, and it will look exactly like a discovery. The deeper worry is about the stars themselves. The entire method rests on the assumption that a type 1a supernova exploding 8 billion years ago was the same brightness as one exploding last Tuesday. If that is not true, if the average brightness drifts even slightly across cosmic time, because the chemistry of the galaxies producing them has changed, then you would manufacture exactly this signal out of nothing. Distant supernovae would look systematically off. You would misjudge the distances, and the misjudgment would grow with distance, which is precisely the pattern that gets interpreted as dark energy weakening. In 2026, Samsuzman Afroz and Suvadip Mukherjee published an analysis in Physical Review D arguing something close to this. They compared the supernova measurements against the sound wave measurements, and found the two do not perfectly satisfy a relationship that geometry says they should, with the mismatch growing gradually as you look further out. Their conclusion was blunt. The evidence for evolving dark energy from the DESI second data release in their reading is absent. A separate team, Sourav Das, Surhud Moore, and Shadab Alam, went after the same seam from a different direction, testing whether the intrinsic brightness of the supernovae might be evolving. George Efstathiou at Cambridge, who has spent decades on the cosmic microwave background, has published his own skepticism about how the sound wave measurements are being interpreted. Deng Wang and David Moda asked directly, in the title of their paper, whether the second data release truly revealed dynamical dark energy, and their answer was not a simple no. When they examined each dataset independently rather than in combination, evolving dark energy was still, on average, mildly preferred over a constant, which is the most annoying possible outcome. The skeptics found a real problem with the combination, and the signal did not entirely go away when they removed it. Meanwhile, the argument moved again in the other direction. A reanalysis of the Dark Energy Survey Supernova program, published in 2026 with an updated calibration of the Type 1A brightness scale, came back supporting evolving dark energy. So the people most worried about supernova calibration went and improved the calibration, and the result survived. I have gone back and forth on this while putting it together, and I think the honest summary is that nobody currently has the standing to close the case in either direction. The evidence is strong enough that it cannot be dismissed as noise and weak enough that it cannot be called a discovery. It sits in the least comfortable region of scientific certainty, which is also, historically, where most of the interesting things have been found. There is one more piece to this that gets almost no attention outside the field, and it is the part I find genuinely unsettling. You might reasonably assume that if the standard model is cracking, all the cracks are connected and one repair fixes everything. Cosmology has another famous problem, the Hubble tension, where two independent methods of measuring how fast the universe is expanding right now disagree, by about 8% and refuse to reconcile. It would be very tidy if evolving dark energy explained that too. It does the opposite. Most of the dark energy models that fit the DESI data push the predicted expansion rate down, away from the direct measurements, which makes the Hubble tension worse rather than better. Solve one, deepen the other. And there is a third anomaly sitting alongside them, sometimes called the S8 tension, concerning how clumpy the distribution of matter is. Measurements of the actual clustering keep coming in slightly below what the model predicts. 3 separate discrepancies. No single modification fixes all 3. Some fixes actively worsen the others. Either at least one of them is a subtle instrumental error that a very large number of extremely careful people have failed to find, or the missing piece of physics is something none of us have thought of yet. The good news is that this does not stay unresolved for long, and that is unusual. Most deep questions in physics are permanently starved of data. This one is about to be drowned in it. DESI has already been extended. Rather than shutting down after its planned 5 years, it will keep observing through the end of 2028, expanding its survey area from 14,000 square degrees of sky to 17,000. More sky, more galaxies, tighter error bars on exactly the measurement in dispute. The European Space Agency's Euclid mission is mapping the geometry of the universe from orbit at a scale nothing has attempted before, using an entirely different technique based on how mass bends light. NASA's Nancy Grace Roman Space Telescope is built specifically to survey wide fields for dark energy work, and it will observe supernovae with a single instrument and a single calibration, which attacks the systematic worry directly rather than trying to stitch surveys together. And then there is the Rubin Observatory in Chile, now operating, which will find supernovae by the hundreds of thousands. The current argument is fundamentally about whether a few thousand exploding stars from several different catalogs can be trusted at the 1% level. Rubin does not resolve that argument by being cleverer. It resolves it by making the sample so large and so uniformly measured that the systematics have nowhere left to hide. We will probably know inside 5 years. Some of the people who started this argument will get to see it settled, which is not something cosmologists usually get. Here is what I keep coming back to. In 1998, 2 teams went looking for the deceleration of the universe and found the opposite. The result was so unwelcome that both teams spent months trying to find their own mistake before either would publish. They checked for dust. They checked for calibration errors. They checked whether distant supernovae might just be intrinsically different, which is the same objection being raised right now, 28 years later, about the same stars. Neither team wanted to be the one to say that 70% of the universe was missing. They said it because the data would not let them say anything else. And that finding, which looked at the time like an embarrassing error, turned out to be the discovery that defined modern cosmology and won a Nobel Prize. So when I look at a signal that should have faded and did not, defended by one group of careful people and attacked by another group of equally careful people, I do not see a science in trouble. I see the exact conditions under which the last big thing was found. We might be wrong about this. The supernovae might betray us. In 3 years, the whole effect might dissolve into a calibration footnote that nobody outside the field remembers. But if it holds, then the force that makes up 2/3 of everything, that we named without understanding, that we assumed was fixed, because fixed was the simplest thing to assume, has been quietly changing the entire time. And we happened to build the instrument that could see it during the few decades in which we were capable of building anything at all. There is a species on a small wet rock orbiting an unremarkable star that has worked out how to measure the fate of the universe. By counting the distance between galaxies, it will never reach. Right now, that species is having an argument about the 4th decimal place. I think that is the most extraordinary thing we do. Thanks for watching. I will see you in the next one.